often the easiest surfaces to plot are functions. Suppose we have a function z equals f of x, y, and we wanted to find a parameterization for this. Well, we can just let u equal x, v equals y, and then z is equal to f of u, v. Or in vector notation, that's u, v, f of u, v. Let's do the example z equals 3 square root x plus y. Let's try and find a parameterization of this. Well, we do exactly this previous trick. The parameterization must be u, v, and then I substitute u for x and v for y, and have 3 square root u plus v. It's as easy as that. Now, I will note that while these are often the easiest, they're not always the most helpful. Sometimes one can use either cylindrical coordinates or spherical coordinates to make a better parameterization. Let's do an example of that. Let's parameterize or find a parameterization Let's find a parameterization for a sphere of radius r. So for this, I want to use my spherical coordinates. I already have them, so I might as well use them. So if I let x be r cosine theta sine phi, y equal r sine theta sine phi, and z equal r cosine phi, where theta is between 0 and 2 pi, and phi is between 0 and pi. Now let's double check that this is indeed a sphere. So we want x squared plus y squared plus z squared to be equal to r squared. And it is so. You can double check that you'll be able to factor out a sine squared from this x squared and y squared. And when you add in the z squared, you'll be able to factor out the phi, or I'm going to nix this explanation. We notice that x squared plus y squared plus z squared is equal to r squared, so it is indeed a parameterization of a sphere of radius r. Good job, us. Suppose I wanted to find now a parameterization of a surface of revolution. This is also fairly easy. Suppose I have the function y equals f of x and want to rotate it about the x-axis. And we want to find the parameterization for this surface. Well, this is fairly easy to do. So now we want to find the y. So for a surface of revolution, we want y squared plus z squared to be r squared, or in this case, f of x quantity squared. Now we can use the same ideas that we did for polar equations to make this so. So if we took r of x theta equal to x cosine theta times f of x, and then z sine theta f of x. This will give us the parameterization for the surface of revolution for y equals f of x about the x-axis. It should be simple enough for you to see how to rotate around the y-axis or the z-axis. I'll let you figure that one out.